Hello, my name is Dror Regev. Thank you for joining me to this session about time variant phase noise analysis of VCOs. We're also going to discuss cross-coupled VCOs in this session. In the previous session, we have treated the subject of energy conservation in the tank by introducing a negative resistance or conductance around the tank that compensates the losses of the tank, and we did not really focus on the nature of this negative resistance and how we really inject energy into the tank. Now we are going to invest a little bit more focus on how we inject energy into the tank. We will do it by injecting current into the tank. So we can open some transistors, as we will show later on, and inject some current into the tank. But we can do it in several ways. Two different ways to consider that we are going to touch here are continuous way. So in the continuous way, we actually introduce current into the tank all over the period. And the other way that we are going to mention here is to do it periodic rather than continuous. So we will try to have some very, very narrow period in the full oscillation period. So very narrow period where we inject current into the tank. Let's compare these two methods. So we are going to do it only quantitatively or qualitatively, sorry. We are going to talk about the quality of these two methods. And the first method, if we understand that when we use an active circuit, it also contributes noise, as we mentioned before. If we inject current during the full period, we inject noise the whole period. And so qualitatively, it looks like we may be adding too much noise into the tank. In the other way, yes, we have a current source, but effectively it's adding current to the tank just a very short period of the full oscillation period. So effectively, it may be adding less noise than the first method. So we don't have a proof here, but it looks very reasonable to use the second method. In actual design, most oscillators do it by injecting current in very, very narrow pulses. And there may be some theoretical proofs or papers about this, but for our discussion we will just use this qualitative comparison. For energy conservation in the tank, we want to introduce current pulses at very short durations that will return the energy that was lost during the full period in the tank in very, very short instant. So we will describe it as a current delta in time domain. And if we look at the tank, and so we inject current into the tank with this current delta, we find that the current through the inductor cannot change instantly. Okay, this is a known physical phenomena. And so this current that we inject must actually add voltage to this capacitor by charging it very, very fast. And this delta V will be actually the amount of charge that is added divided by the capacitance in the tank, which is also another known figure from electrical engineering. The phase of the current that is injected into the tank or the phase of energy injection is also important, as we are going to show soon. So we inject current to the tank to sustain oscillations, and we have the oscillations, the output voltage equals to the voltage around the capacitor, and it's going to be a peak value, amplitude multiplied by a sinusoid, if we just forget for a minute all the losses. And the current in the inductor will be the derivative of this voltage in time domain multiplied by the capacitance. And so it is going to be the same voltage multiplied by omega 0 and C, and the derivative of the sine is going to contribute the cosine. And what we find is that the output voltage, or the capacitor voltage, and the current on the inductor are actually orthogonal. Okay, so there's a 90-degree phase shift between them. And so we can refer to this diagram where the y-axis describes the current on the inductor, and the x-axis describes the capacitor voltage. And basically, where at the time where the voltage is maximal, okay, the current will be 0. So this will be at this time, for example, and we can find it from this very simple expressions. And when the current is maximal, the voltage is 0. And of course, we have times where the voltage or the current can be negative. Okay, and the trace here is describing the different phases that the tank sees during one period of oscillations. And we want to add energy, or we want to inject current into the tank. And so where will be the best phase to do that? And which instant will be the best time to add this current? So we understand that the current that we inject will translate to a delta V around the capacitor. And let's take just a exemplary moment and add this delta V. So basically what we find is that we add another voltage here at this instant, and we increase the voltage by some. We don't change the current because we cannot change the current instantly in the inductor. But let's see what happens to the phase. So we were at that moment at this phase, and instantly we jumped to a different phase. And if we do it in this instance, what we do is we change the phase very rapidly. This is another way of adding phase noise to the VCO. So it's not a good time to add energy or to add current to the tank. We would like to do this current injection in the optimal way. And this is going to be developed soon. Let's examine two extreme cases of current injection or energy injection into the tank. The first case will be called in phase. So when the output voltage or the voltage across the capacitor is maximal at this instant, we are injecting current, and this current translates to voltage delta on the capacitor, and we are increasing the amplitude. Okay, and when the signal deteriorates, we just return to the same point, and we can inject more current in the next period. But when we inject current that translates to delta V at this instant, we don't change the phase. Okay, in time domain, it will be injecting current in the peaks, either the positive or the negative peak. Okay, so this would be the right timing for injecting energy into the tank. Just by contrast, the out of phase case will be either the picture we showed before, or we will inject the current where the current in the inductor is maximal. And in these cases, we change the frequency, we add phase noise. So it's not a good timing. And if we look at time domain, if we inject current at the zero crossing, or where the current is maximal, the zero crossing of the output voltage, we basically move the sinusoid in time domain, and we create jitter or phase noise. So it's jitter in time domain or phase noise in frequency domain. So all oscillators, or most known oscillators, will try to mimic this behavior by injecting current at the maximum of the output voltage. For NMOS VCO topology, we need to remember the energy phase injection that we just mentioned, and by remembering also that the common source has a 180-degree phase shift between VGS input and current output, we can create a situation where if we introduce a sine wave here, we will maintain in-phase injection of current into the tank at the output. And we are going to use this in the next slides to develop the cross-coupled VCO design. Let's examine two common source amplifiers, okay? Back to back, as they are described here. For each one of them, if we have a sine wave across gate source of the NMOS transistor, we will develop an output current that is 180 degrees out of phase, that will sustain energy lost in the tank if it's in the right amplitude, if it returns enough charge into the tank. Why this is interesting and why is it introduced this way? Because in a differential oscillator, the two outputs will be 180 degrees out of phase. So if we take one output and connect it as the input to the mirrored transistor, and do the same with the complementary output and connect it to the other mirrored transistor, we create a situation when we inject enough current, the circuit supports itself for oscillations. So we inject current into the tank in the right time, and we maintain oscillation by returning the output voltage to the other way, the other side of the circuit, or to the mirrored side of the circuit. And this is the basis to understand the cross-coupled VCO topology that is so common in VCO design. The more common and complete way to describe a physical NMOS cross-coupled VCO is described here in this schematic. So we determine the current in the VCO by using a current source, and we see the cross-coupled transistors. We now have the inductors connected this way, so we have virtual ground here. We still maintain the same performance and behavior that we analyzed so far. The inductors are usually implemented as one inductor with a center tap where we can inject the VDD. And the capacitors now can be made tunable by using varactors and by having V-tune here in the middle and changing the DC voltage across these varactors. We can change the resonance frequency and change the VCO oscillation frequency. So this is a very common topology that can be found in books and papers. And just to go back to an idea of the negative resistance that we have introduced before, we can look into this part, the active part of the VCO, and try to analyze the the differential input impedance into this circuit using Kirchhoff laws, as we did a couple of times in the class. And we will find that the negative resistance across these two nodes is going to be -2 over GM, the GM of each transistor. So this is giving us the implementation of the NMOS cross-coupled VCO and the understanding how the active circuit is actually generating this negative resistance we have mentioned previously.